Hi Year13s. In this video we're looking at a concept called rates of change, and this is basically where we apply differentiation in a context to come up with some sort of rate that something is changing. So in this example we're considering the volume of a cube with side of length x, and we're told that it's increasing at a rate of 6 meters cubed per second, and we have to calculate the rate that the edge length and the surface area are increasing when the edge length is 4 meters. So for us to start thinking about this, what we'll do is we'll just draw a little diagram sort of to help us along our way of a cube, or something that at least looks vaguely like a cube. By the way, if you ever come across a cube that's increasing in size at a rate of 6 cubic meters per second, run, because it's not good. You wouldn't want to be near that. Okay, so this cube has side lengths of x, and it is increasing in size, in volume in fact, at a rate of 6 meters cubed per second. So that means the change in volume with respect to time is 6. And the first question, question A, is asking us to find the rate at which the edge length is increasing. So that's asking for the change in x with respect to t. Now, when we're solving these problems, I often consider it in terms of what we want and what we have and what we need. So we want this derivative here for our question. And what we have is this derivative, dv by dt. dv by dt. And so what we need in order to make this equation work out is going to be something that cancels out the dv and something that leaves us with dx on top. And so this is going to be the formulation of our question. So if we need dv by x, then we need some relationship between x and v. And the volume of this cube is simply going to be x cubed. And we can differentiate that. So dv by dx is going to be 3x squared. And because we need dx by dv, not dv by dx, we can reciprocate this fraction. We're treating it like a fraction, and just make it 1 over 3x squared, which is the same as 1 over 3x to the negative 2. And so if we're wanting to know the rate that the edge length is increasing when this length is 4, then we also need to substitute in 4. So let's find dx by dv when x equals 4. And so that will just be 1 over 3 times 4 squared. So that's going to be 16 times 3, that's 30, that's 48. So 1 over 48. So 1 over 48, and that's going to be meters per second, okay, because it's a length measurement. And so now if we just do a little bit of color coding here, this value here, we've worked out a number for it. It's this number here, and let's get another lovely bright color. And this one here, we have a value for it here. And so our next step is just simple substitution. We are going to write 6 times 1 over 48. So that's going to be 6 over 48, which will simplify to 1 over 8. And because we're talking about the rate that x is increasing with respect to time, that's going to be meters per second, which makes me realize that my units here are wrong. That's going to be meters per meter cubed, which is a bit of an unusual measurement, but nonetheless that's what it is. Okay, so that's question A. We've found that when the volume of this is increasing at 6 meters cubes per second, then the length of the side will increase at 1.8 meters per second when the length is already 4 meters. Okay, so let's think about the surface area now. And so we'll go through the same process for surface area. So, A, we want surface area. So that's dv, that's going to be dA by dt. and we have the volume dV by dt, and so we will need the t to remain on the bottom, we'll need the v to cancel out, and we'll need the a on top. So that's going to be the way our work formulates. So we need to relate area and volume somehow. And so let's think about area. Well, area is going to be, of this, is going to be 6x squared. And we already know that volume is going to be x cubed. So we've got x's in both of these, so surely we can make some sort of substitution. So, although we've got different powers here, so what we could also do is we could look at, since we've got area, we could go dA by dx and times that by dx by dv. So actually what we need is dA by dx and dx by dv. Now the good thing about this is we've already got dx by dv. That's what we worked out over here. And so all we have to work out is dA by dx. So let's work that out first. So dA by dx, that's simply going to be 12x. So I've just differentiated this function here. Nice and easy. And when it's 4, so dA by dx, when x is 4, we're going to have 4 times 12, or 12 times 4, which is 36. So now we can just do our sort of color mix and match. So this here is going to go into here. We know that dx by dv is 1 over 48, and we know that this one here from our original question is 6. And so we just need to substitute each of these values. So let's write it out. dA by dt equals 6 times 36 times 1 over 48. So that's 1 over 48, so that's 1 over 8 times 36, or another way of thinking about it is 36 divided by 8, and 8 goes into 36 4.5 times. And so area will be increasing at 4.5 meters squared per second. Okay, so when we are doing rates of change, the key is to think about what you want. So I'll just highlight this: what you want, what you have, and what you need. And in some instances, what you need might have to be more than meets the eye to become what you need it to be. So just remembering here that we actually needed dA by dV, and we got there by changing that around a bit. And hopefully you're familiar enough with the chain rule to see how things cancel out there as well. So have a go at these exercises here, and that should hold you in good stead for understanding rates of change.